Hi, fellow geochemists and geochemistry enthusiasts. Welcome to Geochemist Tea, the only podcast for people who love geochemistry with a side of tea. Our mission is to inspire future geochemists and to introduce our listeners to niche geochemistry topics. I'm your host, Sam Schur, and this month we are talking with Aidan Kitchener to talk about pyrite chemistry's roles in geochemical exploration and how we can scale the results of this chemistry to whole rock data. Aidan Kitchener is an exploration geochemist at Third Planet Exploration Services. Aidan, welcome to Geochemist Tea.
Thanks, Sam. Great to be on the podcast.
So just as much as having experienced geochemists on the show, we love to have early career geochemists. Aidan, can you talk about how you got started in geology and ultimately wound up working in geochemical exploration?
Of course, yeah. So I was lucky enough to have a geology course at college. So when I was about 16 years old, I would have started that. So before university. So before going to uni, I already knew that I wanted to pursue geology. I did another couple of subjects like maths and physics, and I saw geology as the perfect bridge between theoretical science and having a real world application to this, as well as getting out into the field and exploring the world. So that led to me studying a geology BSc and then leading into doing the exploration geology masters at the Camborne School of Mines. During this course, we began to delve into using geochemical datasets in mineral exploration. This was something that immediately took my interest. I was inspired by the depth of understanding you can build of a deposit or an area that you might have never visited in person. So a month or so after finishing the masters, I got my first industry job working on a small exploration project in Scotland. This was my first exposure to an operating drill program and built upon the practical skills required to be an exploration geologist. The following year, things slowed down on this project, and me and the other geologists that I worked with primarily were put in touch with Simon Griffiths, a familiar name on the podcast. Simon was taking on more and more work and needed help with some of the geochemical interpretation legwork. This was an introduction to consulting geochemistry work. It was maintained as a casual job for about a year, picking up work when it was available. And after a year, I decided that the company, Third Planet Exploration, was something I'd like to be a part of, more than being a casual worker. So I proposed the idea of a full-time contract to Simon, and I've been working with him full-time now for about a year and a half.
So this is something that I love, and I've heard this from a few different geochemists at this point, mostly working on the consulting side. But you guys have really championed yourself and just been like, hey, I'm interested in this. I'm doing a good job. I think I can do a really good job. What do you think? And until you really put yourself out there, nobody's really going to think that, okay, we can actually try and do this full time. I think that's really cool. How has it been working as a geochemist thus far? Any thoughts of how all this geochem experience is going to play a role as you continue to work in mineral exploration?
Yeah, so I think the variety is a big part of it. So far, I've had the opportunity to work on projects from probably over 15 companies, and we've also delivered courses with external companies and attending conferences. So it's just given me the opportunity to develop my deposit knowledge of various deposit types from the geochemical point of view, working from projects in South America to Finland, which I've been working in the industry for a few years, and it would have been quite the busy time if I'd have gone and worked on these projects in person. So I've got a lot of varied experience, and you're learning them in a smaller amount of time, but you also get to talk to the experienced geologists that have been on the projects, as well as talking to experienced geochemists such as Simon, and he gives an insight into how to maximize the value of the geochemical data that we are given.
Yeah, and I agree with that so much. And something that I find very addictive about it is just the fact that you get to work on all these projects and all these even different proposals that come out to you, and you get to sit in all these different meetings where people are just like, okay, here's our project. And I find it so fascinating. And I'm just like, yeah, let me do this. This is going to be so interesting, so awesome. It's really cool to have it so early in your career.
Yeah, there's not many jobs where you can go from one continent to another in about an hour.
And especially as a young geologist, a lot of people get put into soil sampling, core logging, and can't really make it out of the core shack. And some people love core logging. I know people that are in their 60s and just love core logging, and good for them. Sometimes it's really hard to break that mold. And yes, it's important to see the core, don't get me wrong. But
Definitely.
from an early age, you've been able to just experience so many things. I think that's just so cool. Any advice for young geologists that really want to get into geochemistry as a young geologist yourself?
Yeah, true. I think reaching out to people is good. The more people you can meet, the better. And most people in the geology community will be happy to give you advice. They're not necessarily going to give you a job as soon as you start talking to them, but they'll point you in the right direction. Attending events, we have, I know this is coming from living in the UK, so we have sundowners in London and Bristol now. And obviously going to conferences where possible. This can help to really grow your network. And once you've met someone in person once, they tend to remember you a lot better. And you never know when the opportunities will arise. I wasn't really expecting to finish in Scotland and then start doing geochemistry. It was just a kind of fell into place. So just,
Such a good point. Yeah, and it's such a good point too, because I think it's great if you go into, say, a conference with, okay, I need to get a job, but every person that you're going to talk to doesn't have necessarily a job for you, or they work for a bigger company and there's a process that you have to go through. So there's that too. So it's much less personal, unfortunately. But if you talk to people, there's going to be at least one person that remembers you, or they know of somebody that is hiring or something. So by just going up to people, introducing yourself, maybe giving a compliment.
yeah.
But you
Make
don't
a
have to
good
give a
impression.
compliment. But making a good impression. That's better. But that's definitely a good place to start. So yeah, don't go into it thinking that everybody's got a job for you, and don't be disappointed is what I mean by that. But just know that people really do remember you. I was at a wedding in I think Thunder Bay, Ontario, and I remembered 3 different people that I had met at the P deck, and it was
Yeah.
just, you just remember these people that you don't really even
It's a
know.
small
So
world,
it's
isn't it?
super small. So yeah, great point. Okay, so I know from how many likes you've given me over the years that we've been doing geochemistry that you're a fan of the show. So I think at this point, you know what tea time is, and I can't wait to hear what you've brought us. So please spill.
Yeah, so for my story, we're going to go back to my first geology job in Scotland. So I was working on site most of the time with my now good friend Harry, and we were staying in what was like a static caravan park. I'm not sure if that translates into America, but
So a trailer park.
yeah, I guess a trailer park. Yeah,
Okay.
a lot smaller
Honestly,
than what you get over there.
I didn't realize that England had, or the UK in general, had
Mm,
trailer parks until I watched, I think it was what, the 7th or 8th Harry Potter film. And there was just
yeah,
this
yeah,
one like shot over a trailer park. And I was like, this is incredible. I had no idea.
yeah,
But
definitely a
everything
thing.
was like cosmodels.
Yeah.
Okay.
Yeah, so we lived up in Scotland, and this was throughout the winter time, so it was pretty quiet up there. It wasn't peak holiday season or anything. So we would come to a Friday night, and the only place we would go would be the only place that was open was a small pub on the neighbouring caravan park. Everything else had closed due to either COVID or just the time of year. So it was usually pretty busy because it was the only one that was open within walking distance of the little town where we were staying. And there wasn't a lot of room inside. So most of the time we would have to sit outside, and it wasn't quite Canada cold, but it was cold enough when you got a cold pint. So we'd sit outside, committed to have our Friday evening pint, shivering in the cold. And after a few weeks of going there, you'd be recognized by some of the locals, generally older folk. And it was the same bunch every time we went there. I think it was their Friday religion as well to go to the pub. So eventually, once we'd had a couple of whiskies with them and got acquainted, they'd start putting music on, and Harry had let out that he could sing. By the end of the time working up there, the Friday night would end in a sing along with all the locals in the pub. And I think there is a video somewhere that I'm not sure Harry knows about.
I love that. I don't even know this guy. What would he sing? I think that's an important question.
Oh, anything. A lot of classic
Anything.
stuff. He can actually sing. I can't, so I
We'll
let him do
talk
most of the singing.
we'll talk one time when we're in person about somebody that we mutually know who loves karaoke and what their favorite
Ah.
song to sing
I
is.
look
So
forward to hearing about it. Probably in Australia.
yeah, exactly. Oh my God, that's great. For this episode, Aidan had a pretty solid idea from the get-go of really what he wanted to talk about, which is the theme of this year's poster that he's going to be presenting at the International Applied Geochemistry Symposium in Adelaide, Australia, which is super neat for me, the topic of this actually, because since my master's, I've been a huge fan of pyrite chemistry and can really talk at length about how the changes that they go from N and to P-type conductors. But that said, we're not going to be talking about that, but we're going to be focusing on using whole rock and in situ pyrite chemistry to examine ore deposits, which is totally different for me, and I'm super excited to dive into it. If anyone hasn't yet read the title of the paper we read for this episode, it is Using Whole Rock and In Situ Pyrite Chemistry to Evaluate Authigenic and Hydrothermal Controls on Trace Element Variability in a Mineralized Proterozoic Subbasement by Magnella et al. 2022. Not yet released, but soon is 3PX's abstract to IAGS entitled Using Drill Sample Multi-Element Analyses as a Proxy for Pyrite Mineral Chemistry in Mineral Exploration and Ore Body Characterization by Aidan and Simon Griffiths, which I'll also post to the website as soon as it's published. Okay, so first let's just set the stage. While focusing on trace elements in pyrite, this paper is essentially all about the Tina deposit. Can you give us some background information on Tina, where it's located, what type of system it is, and why it's famous?
Yeah, of course. So this paper's taking us to the MacArthur Basin in Australia, part of the ISA super basin. The basin contains preserved carbonate and siliciclastic sedimentary rocks that are aged approximately 1.8 to 1.6 billion years. And these have been linked to accretionary events at the time of formation. The rocks in this area are particularly well preserved as well. These rocks, just an interesting fact, contain some of the oldest hydrocarbons that are of Precambrian age. And Tina was the most recent discovered clastic sedimentary hosted mineral deposit when this paper was published, at least. So mineralization at the Tina is a stratiform lead zinc and is hosted by the 1.64 billion year old Barney Creek Formation, the host formation of various other mineral deposits in the region, including MacArthur River. The main stage of hydrothermal sulfide mineralization occurred during burial diagenesis of the host rock and formed primarily via replacement of dolomite in a sub-seafloor replacement hydrothermal setting.
Okay. I've heard about Tina for a long time. I did a study with hyperspectral with a client on it, so I'm a little bit familiar with it, but
familiar already, yeah.
Yeah. But that's a little bit deeper of a dive than I did. I was just like, yeah, you guys have chlorite. No, I'm kidding. It was much better than that. No, that's cool though. Okay, now though, let's get a bit more into pyrite, which is obviously what I'm so interested in. But also, really, what insights at Tina was pyrite able to play in order to reconstruct its diagenetic and hydrothermal history?
Yes, so in the paper they show there were clear subbasin controls on the availability of trace elements within the Tina subbasin, and these can be attributed to orthogenic and hydrothermal processes. So there were two main stages of types of pyrite that they identified during the study, the diagenetic and hydrothermal. So already you can start to think of the exploration implications for being able to identify the difference between your diagenetic and hydrothermal pyrites just from the geochemistry. So these pyrite phases were then ultimately broken down into 5 stages. We had 2 diagenetic stages labeled as pyrite 1 and 3 hydrothermal labeled as pyrite 2. So focusing on the hydrothermal pyrite, we have a first phase called pyrite 2A. This phase formed spherical crystals with a high porosity. Pyrite 2B then formed overgrowths of pyrite onto pyrite 1A, which is diagenetic, and pyrite 2A, the first hydrothermal pyrite. And finally, the least common pyrite phase during the main hydrothermal event was pyrite 2C, which is observed forming overgrowths on pyrite 2B to fill pore space. There are some great images of these relationships in the paper which make it a bit easier to visualize. The interesting point here is that from a mineral exploration perspective is the association of pyrite 2C, the least common hydrothermal pyrite phase, and its association with late-stage replacement of coarse sphalerite, galena, and pyrite, which is present in the higher grade lens.
Honestly, I just want to jump all my questions and start just really quickly. Let's talk. I was like, no, I have to right now stay to the questions because I've arranged them in such a way that makes sense, and I can't go off script. Exactly, because I want to know all the things about the pyrite. But first, the next thing I just really wanted to ask, just to get everybody into the mindset of where we're going here, is to talk quickly about principal components analysis, because that's a big component, no pun intended, of what we're going to be talking about as well in terms of a workflow. So I just wanted to have you quickly define PCA to our listeners and just explain in the context of the paper just how it was such a powerful tool for the authors to both better understand their different phases of pyrite and really how they were able to use the ratio generated from the pyrite chemistry to better understand the trace element chemistry.
Yeah, so PCA is it's a multivariate technique, so we can input as many variables as you like, as far as I'm aware, and this tool will then produce linear trends with these that capture the variability of the data set. So we're essentially trying to reduce the dimensionality of the data set so we can visualize it. So you can take from about 10, let's say, to 2 or 3 on 2D or 3D biplots. These are then output as principal components. So these are the numerical figures you get from running the tool. And the first few of these represent most of the variability in the data. So each input variable, or element in this case, is then given a numerical value to each principal component. The higher this value is, the greater the influence this element has on the variability of that principal component, which is a bit of a mouthful, but it makes a bit more sense
Yeah.
in practicality.
It really
um,
does, but it's good to talk about.
Yes, yes. We begin to get groups essentially of elements that are associated with variability in our data. And that's where the real power in this paper is. And taking a look at the paper as well, the first reason I think this tool was so powerful for them was they used a limited set of elements and they already had a solid foundational understanding of what they were looking for from the data. They'd already looked into what elements were present in the pyrite. It wasn't just to put 50 elements in and hope something comes out, because a lot of the time you just end up with a mess that's a bit incomprehensible.
Yeah, super good point. I guess in this case, what they might have been looking at was say, we know we have these two general groups of pyrite.
Mm,
We're only interested in the hydrothermal, so let's just split that out. So we know the diagenetic has these, for example, 5 elements in it. So let's just remove these from the picture. It's a really good way, I think, in general, when you're doing a principal components analysis to think about things, is that in a way, it can be unsupervised in
mm,
how you're going to get your answer will pop out, if you
yeah.
will. But just like any other dimensionality reduction, there is this supervised kind of piece that goes into it where, as you say, you're choosing your elements. That's a really good point.
Yeah, for sure. It's good to have already a solid understanding of what you want to get from it. And in this paper, they put in, I think it's around 10 elements, and they got out essentially 2 end members from it. So they got a hydrothermal phase that was enriched in thallium, lead, and arsenic, and then a diagenetic phase, which is enriched in molybdenum, cobalt, nickel, and antimony compared to this. So that the hydrothermal was a positive PC1, let's say, and the diagenetic was a negative PC1.
Yeah, exactly. And that was really just then how they were able to generate this ratio from the pyrite chemistry, which is because one, they understood their inputs, and then two, they really saw in those outputs just how
Mm,
strongly the two were partitioning. I always find people that are able to, in a way, really go all Cliff Stanley on us and start to generate these ratios and make this kind of beautiful geochemistry really happen. And
mm,
it really honestly wasn't until very recently that I think Nat Cassiagli showed me just this really simple way that with a PCA, you can
mm,
really start to simply generate these ratios that can be really impactful. And if anybody, like we say, wants to learn more about
mm.
this, read this paper.
Yeah, definitely. I agree with what you say about the ratios as well. It's a way of, if especially if you're putting figures in a paper or if you're presenting it in a more of a company environment, you could plot PC1 down whole, but then it's not in terminology that necessarily everyone's going to understand or know what you've inputted. So, like in this case, they use thallium, lead, and arsenic over nickel and molybdenum, and everyone generally has heard of them, and you'll know then what it's saying. You're basically ratioing hydrothermal versus diagenetic pyrite.
Yeah. And I think too, you talk about it in terms of presenting to a company, and if somebody at the table wants to get deeper into it, it's okay. Then
Yeah.
we had done this. And so you can really take them through step by step the workflow if they're interested. But sometimes people only want the high level, and it's like, here you go,
Yeah.
presented,
Yeah.
something that you guys can use in the future, but we don't need to know. So it can go two ways in terms of a company presentation. So I like that point. It's really good. All right, for our next question, I started writing this question unsure of where or actually what the question actually was. Really, I had so many thoughts in my head as I was reading the paper and knowing where we were going with the topic that I was just like, I need to ask this. And this paper is saying, anyway, there's a lot going on in my mind.
Mm.
But I think the way that I've done this, and I'm going to split this up into a few different stages here, but okay, I want to actually say it all.
Go for
Right.
it.
I love it. Okay, I think by just saying it all at once, it gives really good context. So I'm just going to say it all. Hopefully, maybe you'll go with me and you'll just answer it one by one, but we'll see. So I really appreciate it in this introduction how the authors took my biggest question while starting to read this paper, which is to say the LA-ICP-MS analysis of pyrite is not without some challenges, however, and includes 1, the time-consuming nature of generating petrographic data and development of subjective paragenetic arguments, 2, mixed analyses when analyzing inclusion-rich or fine-grained samples, and 3, heterogeneous reference materials that compromise the accurate quantification of data. So something that kept crossing my mind before actually reading the paper was it okay to use pyrite TINA because it's only diagenetic, which I quickly found out to be untrue, as TINA has at least 5 pyrite stages, which include diagenetic plus hydrothermal. So really, after all this, my question here for you, Aidan, is how can the translation of pyrite chemistry to lithogeochemistry be used when you have multiple pyrite stages? You have this diagenetic, this pre-syn and post-mineralization hydrothermal pyrite, etc.
Yeah, so something this paper touches on briefly as well is looking at the lithogeochemistry in these marine sediments. So they break down using some redox sensitive trace elements and coming up with some kind of proxies for their formations they've got. And then something that's quite powerful is then being able to link these different pyrite generations to these lithology groups. And that's something that we've done as well, and that we'll probably touch on later as well. So I think linking the sulfide, the inferred pyrite species to then a lithology or technically could be something that's not been logged as well. It's just a variation in the trace elements or these redox sensitive elements. You then start to understand where you're getting these hydrothermal pyrites, which of these hydrothermal pyrites is important for your mineralization, but then also almost like a target horizon where you've got the correct chemical lithology that will induce your metal precipitation. So you're almost building a targeting kind of system rather than just focusing in on the pyrite. So you're looking at it a bit of in a broader way. So that example relate to some reduced sediments or sediments with a stronger detrital influence, which are a key pathway for these fluids.
Oh, I love that. That's so cool. All right, so changing gears a little here, I think it would be really neat to talk about the role of pyrite in understanding, as we were just talking about, the redox dynamics, though, in mid-Proterozoic sedimentary environments. The authors had some interesting commentary here, particularly in reference to the lateral zonation of trace elements.
Yeah, so the first thing I'll reference is the isotope chemistry they've used, which is not at all my speciality, so I'll try my best. But so they've used the delta 34 sulfur values as essentially a measure of oxidation state. So where you've got highly positive values of this that correlate with total organic carbon over phosphorus ratios that are also elevated. This essentially is indicating regeneration of organic material during a reduced to eosinic deposition. So you're inferring the environment already. And you can link that from your sulfur isotope data then to what they've collected. I think it was around 70 samples of kind of whole rock data. So looking at those two variables side by side, they've picked out a kind of subformation that's been deposited in a much more reduced to eosinic kind of environment than the other rocks they've seen at the deposit. So it's also introduced early in the paper that you can get lateral variation in trace elements that you'll find in diagenetic pyrite that are influenced by lateral halos of hydrothermally sourced metals in seawater, which are then sequestered by pyrite. So going back to the ratio that they formed from the PCA, the thallium, arsenic, and antimony over molybdenum and nickel ratio, they observe here a vertical variation in this, a vertical zonation essentially. And they've determined that this zonation is actually due to hydrothermal elements, that most of the variation seen is in those first three elements rather than the molybdenum and nickel. So it's not necessarily a diagenetic signature they're getting from this vertical zonation. So the interpretation then follows the idea that the lateral trace element variation in your pyrite can be observed in deposits hosted by the Barney Creek Formation, and this can actually be linked to the individual subbasin formation rather than distal influences. So the subbasin is essentially controlling the variability in your trace elements, which I think they point out highlights a key challenge when trying to extrapolate this data from a basin to basin, because you're getting completely different values, say in this ratio, for example, compared to the region as a whole.
I love it. Super neat. This is such a really interesting paper. Like it just,
It is, yeah.
yeah, again, to our listeners, it wasn't complicated. Like I loved that mostly about it. It was
Mm,
written for everybody, I feel,
yeah, yeah.
because it kept things relatively straightforward while presenting a lot of supporting evidence, but
Mm,
also things that you could apply in the field, like yourself, kind of thing, for our role as explorationists. Everything should have roots in academia, don't get me wrong, but it was just like it gave us these tools, yet at the same time, it was taking complex ideas and allowing you to read it and not needing 3 PhDs to do it.
exactly, yeah. Yeah,
Yeah.
this was one of the first pyrite chemistry papers that I'd read, so it was a good introduction, I think.
Definitely. And for everybody that is unaware, which would be everybody except for Aidan, I definitely sent him like 3 papers on pyrite chemistry that I had to read multiple times for during my own master's, just because I think we just see pyrite and we just always think of it as we did when we were young and it was fool's gold kind of thing. And
Mm,
actually, pyrite can contain a lot of metal, number one, but it's also just this fascinating subject because it's just something that we're, I don't know, I just felt like it's something that we took for granted always, but then you just see how complex it is and how important it actually can be. And there's just such a wealth of literature out there on it. And I don't know, I could go on forever. I love pirate.
mm.
Okay, so now that's actually a good segue
Mm,
because as I hoped it would, the paper actually started to get a little bit into the structure of pyrite. And in this case, how the incorporation of arsenic could influence the incorporation of other elements into its structure. So in the case of other elements like thallium, though, it may not. So this is a whole topic for another episode. Maybe I'll try and find somebody to talk about pyrite chemistry with us because it's fascinating. Honestly, too, maybe it's even a niche or pyrite like
mm.
style podcast that we could do. I don't know
I
what
think
that
we
would be. I don't know if I have time to do it, but pyrite, maybe we get
might have
its
to
own
be multiple
podcast for.
episodes.
However, I'm going to let Aidan off the hook a bit and just ask him what the coolest thing about pyrite you learned since starting to work on this project.
Yes, I think it's going back to what you mentioned about calling it fool's gold and not appreciating it, but not knowing how much of a powerful tool it can be in like vectoring for mineral deposits, for example, and understanding the environment as well that the sediments would deposit in. And reading this paper and the couple you sent me has definitely opened my eyes a lot to how you can use it and then try to then apply it into mineral exploration as well.
Yeah. And I'll just say too, for my end, I think for a long time, it was just like, okay, you need arsenic to open up the pyrite structure because of
Mm,
different substitutions that it requires. And whereas that is definitely a true statement, there is so much about pyrite chemistry where you don't need arsenic. It can either contain metals as nanoparticles or it can incorporate, it's all through charge balance, but it can incorporate other metals into its structure with sector zoning or some other types of zonations where you don't require arsenic. And it's just this absolutely fascinating thing. So everybody should read more about pyrite. It's everywhere. Okay, I guess after our little thing on pyrite, I really want to thank you so much for taking us to this paper because it was honestly, it was a great read. So thank you. That said, I just wanted you just to talk about a little bit about your poster that's going to be at the IAGS because this is something similar, but it's taking the ideas here and applying it to your own project. So tell us a little bit about it.
yeah, like you said, yeah, this was very much an inspiration kind of paper for this poster and for the work. So we were working for a client, and we had some drill core analysis samples from a VMS deposit and obviously lots of pyrite. And so these were just analyzed with it's a complete geochemical characterization package from ALS, which simply means the elements that we've looked at in the paper. Most of these were analysed with 4-acid digest followed by ICP-MS, with a couple even being aquaregious. We're not looking at spot analysis on pyrite anymore. We're just looking at the whole core been crushed and then digested, and it's a complete sample. So based on the background geology, we knew we had marine sediments, we knew we had diagenetic pyrite or potential for it, and then massive sulfides as well. So lots of pyrite. So our poster then walks through how we've used the workflow from the paper using PCA, and then we've managed to find end member elements for our pyrite generations from this data, and we've essentially replicated it but in a different deposit across the world. So the main difference really in the methodology was how we picked out the pyrite, because obviously we couldn't just decide what we were analyzing. It was a drill core, so it was just all thrown into one basket. And we did this using iron sulfur ratios. So where we had an iron sulfur ratio that was plotting along the pyrite line, we assumed that at least the main influence here on your iron and sulfur content is pyrite. So that was basically the best case group. And we input that into PCA, and it gave relatively similar groupings to what in the paper. We had this hydrothermal signature with elements like antimony, and then we had another signature with elements like molybdenum and nickel, which is more of our diagenetic. And we actually had a third one off with manganese and zinc, which we'll come back to in a bit. But then I decided to include a few other groups. So we had about 3,000 samples, and the pyrite subset was probably maybe 10% of that, so about 300. So I wanted to try and make the group bigger and bigger, essentially, to give the PCA the best chance of pulling out the most robust kind of interpretations, because it will look for trends, even necessarily maybe if there aren't necessarily trends. So I essentially just went through iterations of adding in a couple of groups that definitely contained pyrite, but also had slightly higher iron sulfur ratios. So maybe had some more like pyrite in there, or some potentially other element or other minerals. So things got really interesting really when we started to plot this downhole, because this was it wasn't really like a planned project. It was more of a read the paper and thought this could be quite interesting. So when we plotted it downhole, we got these very clear downhole correlations between these essentially 3 end member groups of pyrite we picked out. So we had our diagenetic pyrite at the top working downhole. We had then the first hydrothermal pyrite group, which was associated with what I would call then the main kind of mineralization stage of copper and some gold. And then we had a second hydrothermal pyrite group that was actually picked out in the geochemistry, which was then associated with lead and zinc mineralization. Summarized, we'd picked out essentially 3 end member pyrite groups. We had a kind of mixed bag in the middle, because I went down the route of using a ternary plot, plotting the end member elements that I think replicated the groups the best, and trying not to use things such as copper that's within the mineralization. And yeah, we got 3 very well correlated end members that worked well downhole, and we thought it was a pretty robust interpretation to what was going on there.
That's so neat. I love that. I can't wait to see
Yeah.
the poster.
Yeah, you'll get to see it.
Yeah. Oh my God. I don't even know a question I want to ask about that. That's just a super neat application. And you don't have to say anything specific, but when you talk about you talked about consulting a little bit earlier, like what's in that case, what's the deliverable to the client? Is there something that they're particularly interested in? Is it an exploration style strategy that you're delivering? It doesn't have to be super specific.
Yeah, I think generally speaking, it's a bit like we were talking earlier. We're pairing it with kind of the litho geochemistry as well. So you're building a picture of where these mineralizing fluids were actually focused and the different generations. So you can imagine if you're looking and you've got your horizon where you've determined in your lithogeochemistry, you've got your most kind of favorable host rock, and then you're looking at your pyrite generations, you can already start to tell from the different pyrite generations what mineralization you think you'll have there, even before you've necessarily looked at other rocks. So I think it's building up that ore deposit knowledge and just really solidifying your knowledge of it using geochemistry as well. Something and data that's collected anyway, taking the most value out of it.
So when you talk about all this, it sounds like something very simple that you have dreamed up here. How long, just to bring everybody back to reality,
Mm,
how long was that transition from reading the paper through to playing around with some data, being like, this is
mm,
possible towards delivery to client? How
mm.
long did this entire process take?
Yeah, so this was more, I think, one of our kind of we'd read the paper and we thought this would be quite interesting to try out. And obviously it's not a research project, so it was more of a matter of days maybe rather than spending months and months. I think the most time consuming part, I think when using any data that's not purposefully collected for academia or research, where you've got a larger sample set, is just making sure the data's fit for purpose, making sure you've cleaned it up, and it can be used and it will give robust interpretations.
Yeah, such a great answer. Especially you're saying that you had some macroregion in there, you had some whole rock, you had forest, like
Yeah,
it, not an easy data set to play around with. And then I like the contextualization too of you have days, so you got to make it work.
yeah. If it works, if it doesn't, it's okay.
Out.
Yeah.
Yeah. So cool. I think this has been a great conversation, and I really want to thank you so much for being here, Aidan. And I really hope that you enjoyed being on the show with us.
Yeah, thanks for having me. I've really enjoyed it.
No big deal. Thank everybody for listening to Geochemistry, and a big thanks to Aidan Kitchener for coming on the show, dishing some tea, and showing us how we can use papers and scale geochemistry to mineral exploration for us. Thank you to our sponsor, LKI Consulting, and to It's Water and Coma Media for our music. And I'm looking forward to chatting with everybody next month.